Hi, let's take a look at section 3.3 where we're looking at dividing polynomials, remainder, and factor theorems. The first thing that we'll discuss is this process of long division of polynomials. This is a process that involves 6 steps. I'm going to just summarize the steps. If you'd like to read these more carefully, why don't you pause the video and take a look and read them and take the time that you need. The first thing we'll do is arrange the terms of both what we're dividing by and what we're dividing into in standard form. So that means the exponents on the variable will be descending. Then we're going to divide the first term in the dividend by the first term in the divisor. And that result gives us the first term in the quotient. Then we're going to multiply every term in the divisor by the first term in the quotient. And when we write our result, the product that results from this multiplying, we're going to make sure like terms are lined up. Then we subtract from the dividend, bring down the next original term from the original dividend, and write it next to the remainder to form a new dividend. And this new expression will become our dividend, and we will repeat the process that was described above. So it's a lot easier to actually see this in action, and we will look at this process. Now, this process of long division of polynomials can be used for dividing one polynomial into another, no matter what form the polynomial you're dividing by has. The polynomial you divide by is called the divisor. The polynomial you divide into is called the dividend. The divisor, if you write in fractional form, is the denominator, and the dividend is the numerator. So the division algorithm basically tells us if our function we begin with is f of x, d of x is our divisor, and q of x is our quotient, and r of x is our remainder. These are all polynomials. As long as the polynomial we're dividing by is not 0, then the function that we start with can be written as the divisor polynomial times the quotient polynomial plus the remainder polynomial. The remainder is either 0 or some polynomial that's of a degree that's smaller than the degree of your divisor. And again, we'll look at this when we look at our problem that we're going to review. Now, another process of division is called synthetic division. And you technically don't have to know how to do synthetic division. It's just a shortcut that is derived for a special type of long division problem. So in synthetic division, the polynomial you're dividing by has to have the form x minus a constant. If that polynomial does not have that form, then you cannot use synthetic division. And so what this process does is merely look at the coefficients. So it streamlines what you're looking at. Technically, you're doing the exact same process, but it may not seem like it. So we'll actually look at using this process on a problem and kind of point out how the two processes correlate. Synthetic division is just a special way of writing a long division where your divisor is a polynomial of the form x minus c, so x minus a constant, and you're merely shortcutting and streamlining the way the process looks by only writing your coefficients. So we will look at this process as well. Now, from these two processes, we get two really important theorems. One of those theorems is the remainder theorem. And this theorem basically says if the polynomial f of x is divided by x minus c, then the remainder that you're going to get when you carry out that division is f of c. And that's a really powerful result. So the factor theorem is the other important theorem from this section. And it tells us if I start with a polynomial f of x, and if f of c is 0, then that means that the polynomial x minus c is a factor of f of x. So you can go the other way as well. If you know x minus c is a factor of f of x, then you can conclude that f of c is 0. So we will look at exercise 34, and we'll go over these concepts by working on this exercise. One of the things we're told in this problem is that our equation 2x cubed minus 3x squared minus 11x plus 6 equals 0 is what we want to solve. So in this problem, we're trying to solve this equation. What we're going to use to begin our work is the fact that negative 2 is a 0 of the polynomial, which is the left side of the equation. So notice if we take a minute and look back at our two theorems, if we know that negative 2 is a 0 of our polynomial, then the remainder theorem tells us that f of c is going to be our remainder. So when we take what we, so in other words, if I divide x minus negative 2 into f of x, f of c is going to be the remainder of this division. Now, the factor theorem tells us if f of c is 0, then x minus c is a factor, or if x minus c is a factor, f of c is 0. So essentially the problem is telling us that f of 2, so we want to draw some conclusions here. And we want to see how what we learn in this section relates to this problem. So we're told that negative 2 is a 0 of f of x. Well, we can conclude from that what it means to be a 0 of a function is that if you take that value that you're calling a 0 and you were to replace all the variables in that function with that value, you would get 0. So f of negative 2 is 0. Now let's keep in mind that f of negative 2 means all of the x's in this polynomial are replaced with negative 2. So notice what I'm doing. Every x is getting replaced with negative 2. So the f of negative 2 is actually going to be 0. That's why we call negative 2 a zero of the function, because that value, if that value replaces the variable in the function, the result is 0. So notice what we're able to conclude. If negative 2 is a 0 of f of x, that means f of negative 2 is 0. That actually means replacing all values of the variable with negative 2 results in doing the operations that the function instructs results in 0. Now, the factor theorem tells us if f of c is 0, so from the factor theorem, and I'm going to just call this TFT, the factor theorem, and I'm going to call the remainder theorem TRT, just so I don't have to keep writing that out. So THT, the factor theorem, TFT I meant to say, tells me that since f of negative 2 is 0, I can conclude that x minus negative 2 is a factor of f of x. Now, recall that we typically don't want to write things that have double negatives in them. So recall that x minus negative 2 is the same as x plus 2. So we're actually going to use that. So when we say one polynomial is a factor of another, that actually means that if I divide f of x by x plus 2, the resulting remainder will be 0. So let's use long division. Let's look at what this process looks like. So let's take a look. So I'm going to write out the long division problem of dividing f of x by x plus 2. Notice when I use this division symbol, it does not group. So when I use that division symbol and I want to indicate that I'm not just dividing by x, but I'm actually dividing by the sum x plus 2, because this symbol doesn't group, I have to group the x plus 2 with a parenthesis. So this would be a completely different problem from writing the x plus 2 without the parenthesis. So the process of long division says make sure your divisor, so x plus 2 is the divisor, and the dividend are in standard form. That means the exponents on the variables are descending. So we're going to do our long division process. And then I want to compare this to synthetic division, because it is a problem where you can use synthetic division. So I take the first term in the divisor, which is x, and divide that into the first term in the dividend, which is 2x cubed. The result of that division is going to be written above this line and is called the first term in the quotient. So if I divide x into 2x cubed, I get 2x squared. And notice how I'm lining this term up directly above the term of the same degree that's in the dividend. And now I'm going to multiply. So if you look at the long division process, the algorithm that was written out in this document when we first started, it tells us to multiply this term in the quotient by the entire divisor. So 2x squared times x is 2x cubed. 2x squared times positive 2x is positive 4x squared. And I'm now going to subtract. And I'm going to put this in red. So you have to keep in mind that you are subtracting. A lot of times people start adding. So if you have written and done this correctly, the first subtraction will always be 0. So we're going to just leave that unwritten. Now let's subtract 4x squared from negative 3x squared. Notice how, because I'm subtracting, I need to put a parenthesis around what I'm subtracting so that I realize I'm not just subtracting the first term, but I'm also subtracting the second term. So this subtraction gives a negative 7x squared. Now what some people like to do is they like to change this to an addition. And you can do that as long as you change the sign of everything that you were subtracting. So you can certainly change this to an addition if you change the sign of what you were subtracting. So remember, this was a plus. If I change this to an addition, this becomes a negative. So some people feel more comfortable thinking about this as an addition, and that's fine. But remember, what you were subtracting, each term has to change sign, and the subtraction becomes an addition. So notice, in other words, all signs change, including the subtraction to an addition and the sign of everything you were subtracting. So if that's easier, think of it as an addition. Now let's bring down the next term in the original dividend. And we now have formed a new dividend, negative 7x squared minus 11x. And we're going to follow the same process. So you want to always have in your new dividend the number of terms that are in your divisor. So notice how I only bring down one other term so that I'll have two terms here. So x into negative 7x squared is negative 7x. So negative 7x times x gives me negative 7x squared. Negative 7x times positive 2 is negative 14x. And I'm subtracting this product from the new dividend. And again, you can change signs. If I change this to an addition, then the signs of both of the things that were being subtracted have to also change. And remember, if you've done this correctly, the first sum or the first subtraction, if you think of it as a subtraction, has to give 0. If it doesn't, then you haven't put the right term in the quotient. So negative 7x squared plus 7x squared is 0. I'll leave that unwritten. And negative 11x plus 14x is 3x. Now I bring down one more term from the original dividend so that I have two terms in this new dividend. And the number of terms here have to match the number of terms in my divisor. So I'm dividing x into 3x, and I get 3. So 3 times x is 3x. Three times positive 2 is positive 6. And if I want to change, first of all, remember I'm subtracting. You can certainly just think of it as a subtraction, but you're always welcome to make the appropriate change and think of it as an addition. This one I'm just going to leave as a subtraction. 3x minus 3x is 0, and that always should be the case. That first subtraction should always be 0. 6 minus 6 is also 0. So if both subtractions give 0, I write 1 0 to indicate that. And so we knew we were going to get a remainder of 0. Because remember back when, if I go back up here, remember we said that if negative 2 is a 0 of my function, f of negative 2 is 0. And also, from the factor theorem, actually from the remainder theorem, f of negative 2 gives me the remainder if I divide the polynomial by x minus negative 2. So this actually comes from our remainder theorem. If the polynomial f of x is divided by x minus c, then the remainder is f of c. And so when a c, in this case our c is negative 2, is a 0 of a polynomial, f of negative 2 is 0. So we kind of sound like we're talking in circles, but rewind that if you need to, and listen to that again. So a 0 of a polynomial means that that polynomial evaluated at that 0, which in this case our 0 is negative 2, equals 0. That's why we call it a 0. So negative 2 is a 0 of f of x. That means f of negative 2 is 0. But the remainder theorem tells us that the remainder, when I divide by x minus c, is going to be f of c. So I was dividing by x minus negative 2, which is x plus 2, and that remainder is indeed 0. And remember, f of negative 2 is 0. Okay, so that's long division. Now let's look at this process called synthetic division. And I want to do that right beside this so that we can see how these connect and how it's really it's really long division, but it's a shortcut in writing what's happening. So the first thing I do is I write all the coefficients of the dividend, which is my function f of x. So all the coefficients of f of x are written here. Now I write remember I think of my divisor as x minus c. So if I write this as a subtraction, I had done that here, think of this as x minus c, then the c is the only thing I write in this position. My c in this case is negative 2. And typically that's written in this format. So the first thing I do is bring down, so I write you can think of it as just writing a horizontal line here. And underneath this horizontal line that is written directly underneath the coefficients of f of x, I bring down the first coefficient of f of x. Now I multiply my c, which is negative 2, by this coefficient 2, and I write the product. So negative 2 times 2 is negative 4, and I write that product under my next coefficient above the horizontal line that I've written. And I add the coefficient from f of x to this product that I've just written, and that sum is written below the horizontal line. Now what I want you to notice is that this negative 3 and this negative 4 are actually in the long division, as is the negative 7. So you can see that this is really just streamlining the results from the long division. And I repeat the process. My c, which is negative 2, is now multiplied by this negative 7. That product is 14, and that's written directly underneath the next coefficient from f of x, which was negative 11, and directly above the horizontal line. These are added, and the result is 3. So notice where the negative 11 and the positive 14 showed up in the long division. Notice where the 3 showed up in the long division. Now I'm going to multiply negative 2 by 3. So negative 2 times 3 is negative 6. Six plus negative 6 is 0. So the very last number when you're carrying out the synthetic division is always your remainder. The terms that come before the remainder are actually the coefficients of your quotient. So both of these results tell us the same thing. And using our division algorithm, both the long division and the synthetic division tell us if I divide f of x by x minus a negative 2, the result is 2x squared minus 7x plus 3. So that's actually what that tells us. And notice in the synthetic division, you don't put any variables and their exponents. You streamline the process that's in the long division. So I hope that you can see the connection between long division and synthetic division. Synthetic division only works for a small set of problems. Long division works for any polynomial division problem. Synthetic division only works if your divisor is of the form x minus c. Now the division algorithm tells us that f of x is equal to my divisor times my quotient plus my remainder. So remember that f of x was 2x cubed minus 3x squared minus 11x plus 6. So my function was 2x cubed minus 3x squared minus 11x plus 6. My divisor was x minus a negative 2, which is x plus 2. My quotient was my 2x squared minus 7x plus 3. And my remainder was 0. So the division algorithm says when the remainder is 0, actually the division algorithm says f of x equals the divisor times the quotient plus the remainder. But essentially, if the remainder is 0, the division algorithm is saying the function equals the quotient times the quotient times the divisor. And so you can actually use the distributive property to prove that this really does multiply back to give the function f of x. So the distributive property says multiply x times 2x squared. Really, you're using the distributive property twice. So x gets multiplied by the quotient. Added to that is 2 times that quotient. And now let's do both of these products and add any like terms. So x times the quotient gives me 2x cubed minus 7x squared plus 3x. And I'm going to add to that 2 times the quotient, which gives me 4x squared minus 14x plus 6. So let's combine the like terms here. There's only one x cubed term. Let's combine negative 7x squared plus 4x squared to get negative 3x squared. Let's combine 3x with negative 14x to get negative 11x. And then let's recopy that single constant plus 6. So notice that the division algorithm, as we knew it would, holds true. The function does equal the divisor times the quotient plus the remainder. All right, so this was just for the purpose of showing how you compute synthetic division, how you compute a long division problem, and also pointing out what we get from the remainder and the factor theorem. Now we haven't even really begun the work of the problem. So the problem, let's go back to our exercise 44, is actually telling us to solve this equation given that negative 2 is a zero of the function. And the equation is f of x equals 0, and negative 2 is a zero of f of x. So what we typically would do in a problem like this is we would use synthetic division to write the function in factored form. So in other words, our function is x plus 2 times 2x squared minus 7x plus 3. So notice that synthetic division allowed us to get that result. So we're solving f of x equals 0. What we've done so far allows us to write f of x as x plus 2 times 2x squared minus 7x plus 3. And we're actually solving this factor expression equal to 0. So in other words, we already know something that we learned in intermediate algebra, that the only way this product is going to be 0 is if x plus 2 is 0, or if 2x squared minus 7x plus 3 is 0. So we know how to solve x plus 2 equals 0. We add a negative 2 to both sides of the equation, and that results in x equal negative 2. But our challenge here is, how do we solve 2x squared minus 7x plus 3 equals 0? Well, earlier we talked about solving quadratic equations. That's in an earlier section in the text. One way we can solve these is by factoring. So if I can factor this, then I can solve it by factoring. And if that's possible, if I can factor this over the integers, it's always easiest to solve this by factoring. Turns out the factors of this are 2x minus 1 times x minus 3. And I can also use the quadratic formula to solve this. So you essentially have at your disposal whatever method you prefer to use. So it turns out that 2x minus 1 needs to be 0, or x minus 3 needs to be 0. And this is how I'm going to get the other solutions. So add 1 to both sides to get 2x equals 1. Divide both sides by 2 to discover that x equals to 1/2. So that's one of my solutions. Another solution comes from adding 3 to both sides of x minus 3 equals 0 to get that x is equal to 3. So the solution set, I think a lot of times in Mathematica, in my math lab, you'll be filling in a solution set, and you'll be told to separate your results with commas. So the task of the problem going back to the original problem where was to solve this equation. So we want to give the solution set to this equation. So the solution set contains -2, 1/2, and 3. So what you're going to give in your final answer on this as my MATLAB problem depends on how my MATLAB instructs you to give the answer. If you were on a written exam in the hybrid class, where you do your exams in class in your handwriting, it would be sufficient to just say x equal -2, x equal 1/2, x equal to 3, unless I specifically said in the problem give the solution set. So I'll do what my MATLAB does. I'll tell you how I want you to give the answer. So here we saw how we could have either used long division or synthetic division to get a quotient. That quotient allows us to factor our function. If we can get our function down to linear factors, x plus 2 is a linear factor, or quadratic factors, 2x squared minus 7x plus 3 is a quadratic factor, then we're able to find the solutions, because we can always solve linear equations or quadratic equations.